Hello makers! Today we're going to dive into Arduino simulation with Tinkercad circuits by creating a simple stoplight project. Neopixels are all-in-one RGB LEDs that can be programmed to display a wide gamut of color and are easy to use thanks to software libraries that handle all of the heavy lifting that goes into driving a specific piece of electronics. Thanks to the amazing community of makers that support the Arduino platform, software libraries make integrating sensors, lights, motion, or communications into your project to snap. Simply import the library and call the specific functions needed to achieve the desired result. Tinkercad Circuits has a basic set of libraries to choose from, and we'll see some of those shortly. This project is not just about a stoplight though. We want to have a way to get input from the user so that the time in which each light is on can be adjusted. Just like the real thing, we want our stoplight to have adjustable timing depending on predicted traffic conditions. To get user input, we'll be working with an electrical component many of you are already familiar with, the potentiometer. The humble potentiometer can be found in almost any device with a level control that varies from 0 to 100%. So think of devices with a volume control, such as a pair of headphones, or a stereo system, or even a light dimmer. Before writing any code, let's place all of the components and get them connected. Potentiometers are 3-pin devices, with the outside pins being connected to positive and ground as signified by red and black wires. The middle pin is the signal pin, and will be connected to the analog input side of the Arduino. An analog signal is defined as a signal or information that is represented by a continuously variable physical quantity, such as position or voltage. We'll see in a moment how the potentiometer works and what kind of signal the Arduino will measure. Neopixels come in many different shapes and sizes, and several configurations are available in Tinkercad circuits. Here we're using 3 individual pixels. If we look closely at each pixel, we'll see 3 pins, one for positive, one for ground, and a data in and out terminal. When Neopixels are connected in series, they form an addressable chain where each pixel can be called on individually to display a unique color. This chain starts with the pixel that is connected to the Arduino, and it is assigned the number 0. The data out pin of pixel 0 is then connected to the data in terminal of the next pixel, and it is assigned number 1. This process repeats for each pixel we want to add to the chain. It's worth pointing out that Neopixels consume a fairly large amount of power, and there are some design limitations when using these in the real world. If you would like to know more about their use, please Google search the phrase Adafruit Neopixel Uber Guide. It is the definitive source on using these wonderful devices and should be considered required reading when working with Neopixel-based projects. Now that we're ready to write some code, let's take a look at how potentiometers work and the variable analog signals they produce. In this example, there is a power supply set to 5 volts, a single potentiometer, and a multimeter to measure the output signal of the middle pin. In simplest terms, a potentiometer is an adjustable voltage divider. That is, it provides an output signal that is somewhere between 0 volts and whatever the input voltage is. The analog input on the Arduino will read the voltage outputted by the potentiometer and convert that voltage into a digital value. We'll talk more about the analog to digital conversion process when we write that part of the code. Here we can see as the knob is adjusted, the voltage on the multimeter changes. Arduino code is broken up into several sections, the first of which being library includes, variable declarations, and object initialization. To access the built-in libraries included with Tinkercad, click the file icon in the text editor to open the library browser. Before we include the Neopixel library, let's take a look at the documentation by clicking the external link. The Adafruit website contains a wealth of information on how to use each function within the library, as well as some example code for each. Take time and care to read over the documentation, as there are often very important details contained within, as well as complete starter code samples that can be used to verify the library, Arduino, and connected device work correctly before writing your own code. We'll return back to Tinkercad and click the Include button. Next, we'll use a pound define statement to declare the number of Neopixels in the chain. A define statement will replace any instance of num LED with 3 at compile time. There are other ways to declare this variable, but since you may encounter pound-define statements in other code, I wanted to introduce it here. When learning how to code for the Arduino platform, it will be very helpful to look up functions used here in the Arduino language reference for a complete description on how that function is used. After the define statement, we have three variables of type integer that will represent the analog pin that is connected to the potentiometers, one for each color. Comments are defined by two forward slashes and give us the opportunity to write something descriptive about the code just written. Get in the habit of putting comments in, as not only will they help you remember what a segment of code does, but also others who might later see or use your code. The next set of variables will contain the time each light will be on. Note that time in Arduino world is measured in milliseconds, so 5,000 milliseconds is equivalent to 5 seconds. Again, these variables are of type integer and represent the initial value that will be used in the lighting sequence. We'll write a function later that will change their value based on the input signal of the potentiometer. Next, we'll declare LED pin as 11, which corresponds to the Arduino pin connected to the Neopixel chain. Some of you might be thinking, why not just enter these numbers in later when we need them? Why create so many variables? The practice of using variable names in code as opposed to the explicit value means that should anything change, perhaps using more than 3 LEDs, or maybe having to use another pin assignment, all that needs to be done to update the code is to make one change to the variable declaration. Using variable names as opposed to numbers also makes the code more readable and easier to understand. It's easier to read red, yell, or GRN when addressing the specific LED than it is to remember which number they are in the chain. The Arduino platform is based on the C++ language, and as such is referred to as an object-oriented language, albeit with some limitations since the code runs on a microcontroller as opposed to a computer. What this means is that data and functions are organized into objects as opposed to separate elements of code. Think of objects as a container that houses all of the logic and data for a specific process. In our case, we're going to initialize an object that is responsible for controlling the array of Neopixels. Let's take a look at the library documentation to see exactly how to initialize the object as well as the properties of that object we'll be able to access. I'm going to call this object stoplight. Inside of the parentheses are parameters required by the object. The first parameter is the number of LEDs, which we previously declared with #define as num_LED. The second parameter is the Arduino pin connected to the LED chain, and the remaining parameters are specific to the model of Neopixel we're using. The end result of this statement is that we now have an object called stoplight that inherits all of the properties of the Adafruit_Neopixel library. We'll see in the next code section how that works. After variable declaration and object initialization comes the setup function. Setup is present in all Arduino programs and contains code that runs only once after power is applied. First, we call stoplight.begin, which activates the underlying code that communicates with and controls the Neopixel chain. Think of .begin like starting a car. Next, we want to set the color of each pixel by using the setPixelColor function. SetPixelColor takes 4 parameters, the first of which being the LED number in the chain, and the remaining 3 are red, green, and blue values that make up the desired color. RGB values range from 0 to 255, so red would be 255, 0, 0. We'll repeat the function call for yellow and green LEDs by copying the code and changing the appropriate parameters. According to the Adafruit library documentation, we need to call the function show to get the LEDs to update with the new color data we entered. So the next line of code is stoplight.show. After the LEDs turn on, we want to have a few seconds to observe them to ensure everything is working correctly, so we'll use the delay function to pause the program before continuing. Delay is a function that's part of the Arduino core language, and we'll use it later to control the timing of the light. After the lights come on, we call stoplight.clear to set all of the LEDs to off, followed by another call to stoplight.show. Finally, let's add a statement that turns on the serial communications feature of the Arduino so we can have the Arduino send data to the computer that it's connected to. This is accomplished by using the serial.begin statement, with the connection speed as a parameter, in this case 9600 bits per second. Serial is also a built-in Arduino function, so to learn more about it, please see the Arduino language reference. We'll use the serial monitor later to print the values of the stoplight delay times when they're changed using the 3 potentiometers. Now that setup is complete, we're ready to move on to the core of the program, the function called loop. Loop-like setup is present in all Arduino programs, but unlike setup, it runs forever. Depending on the nature of your project, it can be helpful to run the program now and observe the setup code execution to ensure everything is working properly. And it looks like there's an error. Fortunately, this is one that's easy to track down as a parenthesis that is backwards. After making a quick correction and running the simulation again, we can see that 3 stoplights turn on with the correct color and then turn off, just as the code was written. The logic behind a stoplight is pretty simple, and the concept of breaking down that logic into blocks of code is the same no matter the complexity of the project. First, the green light comes on for a specified period of time, followed by yellow, and then red, with the sequence repeating itself so long as there is power. First, let's copy some code we've already written for setting the pixel color. With the green pixel set, the next bit of logic is to call the show function, which pushes the new color to the pixel array. The delay function is next, which will pause the program for a specified time each light should be on. It's worth pointing out the delay function causes the Arduino to literally do nothing for the specified time, so while it's useful in simple programs, there are more efficient ways to achieve precise delays while still letting the main loop code run. The remainder of the green light code block is a call to the clear function to turn the green light off, followed by another call to show. And that's it. The logic for yellow and red are identical, so we'll copy and paste the code already written and make a few parameters changes. Let's run the simulation and check to make sure everything works as intended. Green, yellow, and red. Perfect. There's one more feature that needs to be implemented, and that's the variable timing controls using the 3 potentiometers we set up at the beginning. To do so, I want to introduce the concept of writing a custom function. For simple functions, the declaration generally happens after the main loop. That is to say, if I had 2 or 3 functions, I could place them at the bottom of the code. For more complex projects, the additional code could be written in a separate file and included as a library. Think about all the functions included with the Adafruit library. Let's call this function setLights. And the variable we want to update is the delay time for each color based on the position of the potentiometer. To accomplish this, we're going to need to read the value of the potentiometer using the analog read function, and then map that input value to a desired time range using the map function. Both analog read and map are part of the core Arduino language, and as such are documented in the Arduino language reference. Map takes 5 parameters: the value to be mapped, the minimum and maximum value that can be, and finally the new minimum and maximum value to map to. In this case, we're going to pass the result of the analog read directly into the map function. Analog read senses the voltage on the middle potentiometer pin and performs an analog to digital conversion of that voltage. In this example, the voltage can vary from 0 to 5 volts, and the output of the conversion will vary from 0 to 1024. An analog signal of 2.5 volts will result in a digital value of 512. Now, if we pass this value to delay, and delay works in milliseconds, and 1000 milliseconds is equal to a second, clearly that won't work. The map function will take the digital representation of the potentiometer value and scale it to a minimum and maximum value we enter. Let's say 1 second for the minimum and 5 seconds for the maximum. So we'll enter in 1000 and 5000 for those values respectively. While serial communication is more of an advanced topic, the concept of sending variable values to the computer in which the Arduino is attached to aid in troubleshooting is extremely helpful. In this example, we'll use the serial print and serial println function to output the new delay value to the serial monitor. With a quick copy and paste, we can make a few simple edits to apply the code just written for the yellow and red lights. Now that the function is written, we need to place a call to it in the main loop at the very end, as it will be the last bit of code to run before the loop starts anew. I think that's it. Let's go ahead and run the simulation and observe the behavior of the lights as we adjust each of the potentiometers. In the serial monitor, we can see the new settings for each delay value as the main loop cycles back to the beginning. I hope you've enjoyed our introductory look at Arduino simulation using Tinkercad circuits. Join us next time where we will be developing an electronic dice circuit using the concept we introduced here. As always, if you have any questions or would like to know more about electronics, join us in person at Exploration Commons or visit us on the web. Take care.